Hello there guys, this is Teacher Krishna and welcome to our next class for the third unit. This is a class that is part of Big Hive School and of course it is for 10th high school. Just like you know, this is our subject, Physics 1, and we are working on week number 23 today. So let's go over our presentation. Remember to have your notebook with you in order to make today's summary. And of course, remember that it's very important that you include the following parts in your summary. Include date, end in mind, title, summary, and of course some extra decoration around. Today we are going to study topic 3.02, which is Newton's second law. And the end in mind for today is the following. Students will be able to understand and describe Newton's second law by completing several application theoretical and physics problems. Alright, let's continue. And here you have a small summary of the activities that you need to complete today. So, you need to watch this YouTube video, of course, and make a summary in your notebook. Second, you need to read topic 3.02 and complement your summary. You have to focus specifically on page number 3 because you need to complete the exercises in page number 3 of this topic. Just like every week, I'm going to give you some examples of how to apply the theory that we are learning as well as the formulas and everything, but it is always necessary that you can practice by your own, so make sure to complete those exercises in your notebook as well. Lastly, assessment. You need to complete the assessment for topic 3.07 in Agilex. And those are basically the activities that you need to complete today. So let's continue with our topic. Just like I mentioned before, today we're going to study Newton's second law. And how can we relate Newton's second law to the picture that we have right here of a man that is trying to pull his car because it might have some malfunctioning around? So let's analyze a little bit of the theory of the Newton's second law, and then we're going to go back to that picture. So this theory states that the acceleration of an object is directly proportional to the net force acting upon this object, and it is inversely proportional to the mass of the object. So it might seem a little bit complicated just to state it in this way, but let me explain it or word it out for you. So first of all, we are considering two important aspects. We have acceleration, and of course we have net force. Alright, so we know right now that the car is not moving, probably because, I don't know, he has some problems with the battery. So of course the acceleration of the car is 0. But right now what happens if we start adding a net force? Like the man right over here came down from his car, and of course right now he is pulling his car to the front. Alright, so right now he is adding a net force to the car. But there is something very important that we need to consider as well, which is the mass. Because the higher the mass of an object, the higher the force that the man needs to apply to the object in order to add a certain acceleration to it. Alright? So that's basically it. We have an object that may or may not have an acceleration. We have a net force that is being applied by a person or by another object. And of course, we need to take into consideration the mass. Those are generalities of the Newton's second law. And here we have a small formula that of course represents this law. And we have an explanation of what each one of these letters stand for. So we have that acceleration is going to be represented by A, and it is going to be expressed in meters per second square. We have net force, which is going to be represented by letter F, and it is expressed in newtons. And lastly, we have mass, which is going to be represented by letter M, and it should be expressed in kilograms, right? So let's continue. Oh, now I need you to run the simulation that you have in page number 1 about the Newton's second law and write down a small analysis. So basically, the simulation that you are going to find in Agilix is about like a pulling rope game, where the more people you add, the different acceleration and direction you are going to find there. So go right over there and go to the simulation on Agilix. And of course, when you generate your analysis, of course, make sure to pay close attention to the acceleration, to the net force that is being applied, and of course to the mass of the object. Once you are done with the simulation, you can come back to the video so we can continue with our class. Alright, so welcome back. And besides the analysis that you just did now, we're going to have some application problems. So let's go over some of them. We have the first one right here. It says, as mentioned in the introduction, most motion we observe undergoes changes. Think about leaves falling from a tree, cars going down the road, and a tennis ball hit across the court. These are just some examples of motion that have probably observed, that you have probably observed. So letter A says, in your own words, explain the cause of an object's change in motion. Well, since we are talking about the second Newton's law, then I could explain that we're going to take into consideration that at first we have an object that has a certain mass. And when this object starts moving, or it undergoes through acceleration, what's going to happen is that there is a force that is affecting its motion, right? But of course, the force that is affecting its motion has to be considerably higher than the mass of the object. So in this case, we can actually move the object. That's the way I'm going to explain the changing motion of objects through the second Newton's law. And let's go with letter B. In your own words, what causes an object to be motionless or at rest? So there is a very typical mistake, and people usually say that when an object is in rest, it means that it actually has no forces acting upon it. But this is completely wrong, because when an object is just staying still, it means that the forces that are acting upon that object are balanced. Like, let's imagine your cell phone right now. Your cell phone might be on the table, but it is not moving. So how is it possible that there are forces that are acting upon it? Well, remember that since we are on Earth, we have gravity all around. So gravity is actually pulling your cell phone down. But actually, there is another force that is somehow pushing the object up, which is the force that is being created by the table where it is at. So of course, gravity is pulling it down, but the table itself is sort of pulling or pushing the cell phone above. So because both forces are balanced, then the cell phone is motionless, right? But remember, even though an object is in rest, it means that the forces are balanced. Alright, let's continue with practice number 2. We have Newton's second law is concerned with forces acting on an object. So, letter A, you've probably studied the term force in other classes. In your own words, what is a force? Well, in my words, I can tell you that force is like energy. Energy that is going to act on an object. And, well, in different books, I have read that force is also defined as push and pull. But at the end, it's the same. It's energy that is going to create motion, or that is simply going to act on an object. Letter B, true or false? An object at rest has no forces acting on it. Explain your answer. Well, pretty much that's what I was explaining in the previous part, where I mentioned that, in fact, even though an object is in rest and it is not moving, there are forces acting upon it. But the forces are balanced. Alright, and it says number 3, consider a book at rest on a table. What are the forces acting on the book? Oh, well, this is well the example that I was giving you with the cell phone, right? So of course the weight of the book is being pushed to the center of our planet, right? Because pretty much what's happening is that gravity is acting on it, but the reaction force of the table is actually going up. And when it is balanced, it just stays in the rest position. Let's go with some key terms that you need to remember. So acceleration. It is a change in motion due to an imbalanced force. It considers the change in velocity with time. Of course, this is one term that we have already studied. What is mass? It is the amount of matter of an object. We also have a very important term that we are going to continue using, not only in this class, but in other lessons. So it's very important that you pay attention to this. So when we mention that something is directly proportional, what does that mean exactly? It means that while one quantity increases, the other does as well. That's very important to consider. So they are like dependent on each other. So if one starts going up, the other one does as well. And also we have inversely proportional. It means that while one quantity increases, the other one decreases. So just like with directly proportional, we have two forces that are dependent on each other. But the difference is that while one of them goes up, the other one is going to go down. We also have force. It can be defined as push or pull. And lastly, we have net force, the resultant force of all the ones that act upon an object. Alright, so now we're going to have an analysis of the second law. So right over here we have a pulling game, just like I was mentioning in the simulation that we had before. So let's analyze it a little bit more. So then Newton's second law analyzes the relationship among net force, mass, and acceleration. Of course, right over here, we are going to have all of them. We're going to be having, for example, net force, which is going to be created by the force that each one of the people from the picture are producing. We are going to have mass, which we consider the mass of the rope, and we can consider the mass of each one of the people that we have right here. Alright, and lastly we have acceleration. So in what direction exactly is the velocity going towards? Right, and we have the net force is directly proportional to the acceleration of the object, of course. So depending on the force that is being applied from both sides, it is going to affect the acceleration. So if we add more force on the right, of course, then we're going to have an acceleration that is going to be heading to the right. But if we add more force in the left, what's going to happen is that the acceleration is going to start heading left. Alright, we have the object will follow the direction of the acceleration, of course. Because if more people are pulling to the right, then the acceleration is going to start acting to the right. And the same thing will happen on the other hand. We also have the acceleration is inversely proportional to the mass of the object. Totally. So right now we are considering that the acceleration of the rope is constantly changing, right? Depending on how much people there are and the amount of force they are putting on the rope. But what happens if what they are trying to move is not a piece of rope, but what they are trying to move is a car? So, of course, we are not going to produce the same acceleration in the rope because, one more time, acceleration is inversely proportional to the mass. So basically, if we increase the mass of the object, it is going to cause the acceleration to decrease. And the same thing, if we drop the amount of mass, we are going to increase the acceleration of the object. That's how we are going to make an analysis of the Newton's second law on a pulling rope game. Alright, and we have some other application problems. And the first one, Skelly the skater, total mass 25 kilograms, is propelled by rocket power. So it's asking us to complete table number one, and of course we have to neglect the resistance, and we have a letter B, complete table two for a constant 50 newtons resistance. All right, so let's go with the first one, completing table 1 by neglecting the resistance. So right over here we already have our formula, which is acceleration equals force divided by mass. So in the first one, we have that acceleration will equal the force, which will be 100 newtons on the first section, divided by the mass of the person, which in this case is 25 kilograms, which of course we're going to get a result of 4 meters per second. And this is something very important, guys. So whenever you divide newtons divided by kilograms, the result is going to be meters per second square. It's better if you write it down in your notebook so you can remember about it. Alright, and of course we will have to complete the second one, which will be for 200 newtons, but it will be pretty much the same. Instead, adding a force of 100 newtons, we are going to add a force of 200 newtons. So 200 newtons divided by 25 kilograms is going to give us a total amount of an acceleration of 8 meters per second square. Alright, and what about the second part? Right here in complete table 2 for a constant of 50 newtons resistance. Well, whenever we have two different forces, we need to consider them. And remember that resistance means that it is a force that is going on the opposite direction where the person is heading to. So in this case, on the first part, we have a force of 50 newtons, right? Which is the force that is being applied by the sort of rocket that the person has on his back. But right now, remember that we have a resistance of 50 newtons as well. So 50 newtons of the force that is being applied minus 50 newtons, that is the resistance, divided by 25 kilograms is going to be the resultant acceleration. It'll be 0 meters per second squared. Alright, and you can actually do the same with 100 newtons and 200 newtons in order to complete the rest of the table. Alright, let's continue with this one right here. Suppose A is still a 1 kilogram block, but B is a low mass feather or a coin. Compared to the acceleration of the system in 2, the acceleration of A plus B, here is less, more, and is close to 0 and close to G. In this case, the acceleration of B is partially, particularly than a free fall constraint. So let's analyze the first one. Compared to the acceleration of the system in 2, the acceleration of A plus B here is less, actually, and is close to 0. Yeah, probably you can notice that this block right over here might be heavier than the feather or coin, but it means that when it is close to 0, it means that it is not moving at all. And then number 2, in this case the acceleration of B is constrained. Yeah, it is not the one of free fall because nothing is falling, and since it is close to 0, it will be constrained. Alright, let me go with practice number 6. A ball rolls down a uniform slope ramp. Acceleration is decreasing, constant, or increasing. Letter B. If the ramp were steeper, acceleration will be more, the same, or less. And when the ball reaches the bottom and rolls along the smooth level surface, it continues to accelerate or does not accelerate. So in the first one, acceleration is constant. Yeah, what is increasing actually is the velocity of the object. But remember that acceleration will remain the same. Number 2, if the ramp were steeper, acceleration will be more. Of course, if we are actually generating the ball to move faster, and of course we are increasing the acceleration of the object, it will be more. And lastly, we have number 3. When the ball reaches the bottom and rolls along the smooth level surface, it does not accelerate anymore. And if there are more forces, I will say that I will stop accelerating. Alright guys, so that'll be pretty much today's lesson for today. And thank you a lot for coming to today's lesson. And I will be seeing you during the live meet that we are going to have in a couple of minutes. Alright, so always take care of yourself guys, and goodbye.